Hi, everyone. My name is Cameron Lerch, and I am a third-year PhD student in mechanical engineering and material science here at Yale. And today I will be giving you a rundown of the Intelligent Autonomy Lab. Like Matt said, we are a robotics lab. The Intelligent Autonomy Lab, here's a picture of us. You can see my dog Scotch hanging out there. You'll get to see him in a little bit too. Our lab focuses on artificial intelligence algorithms. And what that means is that we write programs that control robots and give robots the ability to make better decisions about their environment. So we try to help guide robots using their sensors or other information that they can get from their environment to help them make decisions. We use a variety of different programming techniques, a variety of different languages, and a variety of robots. So some of the topics that our lab is interested in include search and exploration. So here you can see a simulation of a little robot driving around on this map. And it's sort of bumping into these objects. And as it's moving around, it's gaining a better picture of where these objects are. So you can see at the beginning, it has no clue, but as it keeps bumping around, it's getting a more and more informed map of what the world looks like. We also do some work with bio-inspired robots. So here you can see a simulation of a mouse. And this project was trying to understand how mouse use their whiskers to sense the world around them, even when they don't have eyesight. So we have some other bio-inspired robotics projects as well. This one is the one with the mouse. We also do some stuff with robotic cooperation. So this is how swarms of drones can sort of interact with each other. So here you're seeing a swarm of little quadcopters sort of flying in the shape of a Y. This is a demo that you'll get to see in person here in a little bit. We also study articulating robots. So we study robotic movement. Here you can see sort of a funny video of a dog walking robot balancing and walking on two legs. And we also study, grasping and manipulation. So here you can see a video of a simulation of a robotic hand sort of moving a die around, trying to get it to a specific orientation. And also a real video of a robotic arm moving this little picture cube around and trying to get it to a specific orientation. So why is our work important? Well, robots, as some of you may know, are going to be a very important part of our future. And the part that makes robots function is their intelligence, and that is what we focus on. So we focus on how the robots are programmed and controlled to complete their tasks. Some areas where robots can make a really big impact include search and rescue. So if, for example, a building collapses, we are trying to develop algorithms to send robots in that can go automatically search through all of this rubble and hopefully find people. Also, surgical robots. This is a picture of the Da Vinci surgical robot. It's a really fancy, very expensive robot that brain surgeons and other surgeons spend a lot of time training on and using, as well as space exploration. So this is a picture of NASA's Perseverance Mars rover, just up there doing its thing on Mars. But you can imagine also robots that will send maybe to other planets that might do mining, or to asteroids or that type of thing. So what kind of work do I focus on? I enjoy search algorithms. So basically, how can we optimally search an area while satisfying a variety of constraints? So what that pretty much means is I like to use the example of maybe sending a robot into a room and you don't know what the room looks like ahead of time. And you want that robot to sort of be able to search the room without running into things. And I also like to work on cooperative robotic systems. And so the main question here that we're interested in is how can we control robots of various types to work together to complete a common task? Here are some of the robots that our lab has. So we have a Franca Panda robotic arm, you can see moving around. We have an Allegro robotic hand. We have a Unitree A1 robot. This is a little dog walking robot. We have these BitCraze Crazy Flies. These are these small little drones, and I'll show you one of those in a little bit. We have an iRobot Roomba, and you probably are familiar with the little vacuum cleaning robots, but they have a lot of sensors that are very useful. So we have one of those. And we also have very high performance computers to help us run some of our more advanced algorithms. Okay, so I'm going to switch over to my iPad and show a couple of demos, and then I see I'm behind on chat, but I'll go through and ask. People can ask questions, and I'll answer everything. So let me switch over to my iPad. Awesome. So the first demonstration I'll show you is a demonstration with our robotic drones called Crazy Flies. So they look like this. They're real small. They can fit in the palm of your hand. Oops, sorry, it's kind of hard to do. They're really small, and they have a lot of really unique sensors on them that make them very useful for our research. So I'm going to show you a little demo. Okay, so you're going to see these drones take off and then fly in the shape of a Y here. It is possible that one of them might just kind of scurry off and do its own thing, but that's okay. Right now, I'm just waiting for the parameters from the computer. Here they go. So you can see they're sort of in the, yeah, that happens sometimes. You can see they're sort of in the shape of a Y here. And after a certain amount of time, they're going to go ahead and land. Perfect. So yeah, sometimes with robots, you can have sort of random issues that come up, like this guy's upside down. These guys, that's sort of part of the focus of our research is how can we program these robots to be better. And then the next thing I'll show you is our robotic dog. So let me get this started. Sorry for all the movement. Okay, so you can see him sort of get up. All righty. And then let me turn the lights on so we can see this guy a little better. And I'll show you him sort of moving around. So right now he's in a stationary mode. This is what the controller currently looks like, but this isn't how we would actually do our research. So this is just sort of like a remote control robot at this point, but our research is more like writing a program on the computer and then sending it to the robot to run autonomously on its own. So you can see as I move this guy around. Oh, yeah, sometimes he just falls over. I just have to like reset him here. Sorry about that. It seems to be the first time he stands up for the day, he seems to just get a little wobbly, tip over, but he should be good for now. I made him look a little bit too far here. Once he stands back up, I'll show you a couple of different modes that he has. So the first mode is he's going to keep his feet stationary, and I can make him look around. And then the second mode, I can make him start. Oh yeah, there he goes. So in this first mode, I can sort of angle him. You can see there's a bunch of different motors on him controlling him. I can make him squat down, stand up, and if I push this button, I can make him move around. So he's gonna sit here and he's gonna stomp his feet for a while. And this is gonna let me actually control him and walk around. The reason why he stomps his feet is because he has little force sensors on his feet, and that's how he knows where he is. So you can see he moves around. I can make him back up. He is very agile, yes. And yeah, so we hope to use him for a variety of different research tasks. I can make him I can sort of make him stop. Oops. Let me make him back up here. There we go. Yeah, what do we mainly use this guy for? So he has a bunch of different sensors on him, and including this fancy camera right here on top. That's called a LiDAR sensor, as well as a bunch of cameras right here on his face. And with all of these different sensors, we can study how we can use these sensors on a walking robot to move around and sort of feel out what its environment is, and also to autonomously make decisions about its environment. So yeah, it's pretty neat. Can make it squat down. There he goes. Yeah. And then the last little robot that I wanted to show you here, we don't have it turned on right now, but this is our robotic arm. It is pretty big. You can see my hand for scale. And this is a very precise robotic arm that we can attach the robotic hand to, and we can do a lot of different manipulation tasks and that sort of thing. So let me hop back over to my computer.
All right, that was really cool. As Cam logs back on, I think we'll have some time to ask a few of the questions that we got from the chat, if that's okay.
So
I mostly
catch up on chat. I don't know if I went over time or not.
No, you're good. I collected questions for you, so I can just ask a few of them. Mostly amazement is the main thing. Can you write in the chat though the name of your lab?
Yeah, sure. I will do that.
Thanks. Yeah, and then as you do that, a couple other questions we had was, can you get one of those small drones? Are any of these robots that you showed us commercially available?
Yeah, so they are all commercially available, I believe, but they're all pretty expensive. So like, for example, for the drones that we use, these guys, they have a lot of special things on them that make them really good for research. They have they enable us to program them in special ways, and so that makes them a little bit more expensive for what you would want to do, or for what a user would want to do at home. But there are plenty of drones. I mean, these are, for example, each drone here is about $250 is the base price. But we have special sensors on top of them that make each of these about $500 or so. And I think we have a total of 10 of those for the swarm. The robotic arm, I'm not exactly sure if that is publicly available, but the robotic dog is publicly available, but it's also very expensive. The one that you just saw, I think, is about $15,000. So they're more for like enterprise research type of things.
Okay, and then I guess the next question was, what does the Franca Erica Panda do? That's the arm, correct?
Yeah, so that's the robotic arm. So it's special because we can a lot of tasks in the real world involve some sort of grasping or manipulation. I mean, think about how many times throughout the day you walk around and you use your arms for doing something, right? Well, the goal is we need to be able to better understand how to program a robot to mimic the motions of our arm, and that sort of thing. We can also attach a robotic hand to it. So one surprisingly difficult task for robots to do is open a door, autonomously open a door, which means they make the decision to open the door on their own. And it's sort of hard to tell a robot how to, where a door handle is, how to recognize what a door handle might look like, and also to know that it needs to open it to get to the other side. So by having a robotic arm and a robotic hand, we can sort of like explore these difficult problems a little more.
We have a question from Claire in the chat. Is the robotic dog currently able to see things with those sensors and react, or is that what your project is working on?
Oh yeah, that's a great question. So what you just saw was me controlling it with that remote control, but that's 100% what we want to use those sensors for. So that's what our research will be working on. We have access to all of this sensor information. And one of our questions is, how can we use that sensor information? How can we use that sensor feedback to help the robotic dog make decisions about what to do? For example, if we had a set of stairs here in the lab, and we wanted the dog to walk up the set of stairs, we would want to be able to detect that the stairs are there, and then use some of those camera, some of the sensors that are on the robot to help us actually be able to move and control the robot up the stairs.
Okay, I think I'm just gonna ask you one more quick question, I guess, kind of off of this. So is your research more programming, or are you building things in lab?
Oh, that's a great question. So we are a controls lab. So we are mainly focused on the programming aspect, but we do work really closely with collaborators that do a lot of design stuff. And we also will have we're a brand new lab, so we're still getting some equipment, but we're going to have 3D printers and that sort of thing, so we can build any sort of thing that we need that might be custom. So we do a little bit of design work, but 95% of all of our work is programming.
Fantastic. Okay, thank you so much for sharing all of this with us. Yeah, that was awesome. I think we're now going to move over to Conor and to their lab. Thanks so much.
Yeah, thank you. If anyone has questions, I'm going to put my email in the chat. If anybody has questions or wants to reach out, you can also just email me a question, and I'll get back to you with the answer when I get a chance. So, wrong keyboard. There's the perfect.
All right. So if we're ready, I'll go ahead and get started. My name is Conor. I'm a graduate student in the group of Professor Hailiang Wang here in the chemistry department and Energy Science Institute at Yale. And so I'm very excited to be presenting to you guys today and telling you a little bit about the type of research that we do in our group. Specifically, we're interested in trying to convert solar and wind energy into chemical energy. And the way that we're trying to do this is by reversing the combustion reaction. And so some of you may know, or maybe all of you know, what combustion is, or what that chemical reaction is. And so we'll go into that here. But first, I'd like to just introduce our lab. So here is Professor Wang. He's very handsome. And here's our group. We're all very good looking, I think. And we're a chemistry and material science lab working on energy conversion and storage. And we're part of this energy Department of Energy hub. So we have a lot of funding from the federal government, the Department of Energy, that is focused on funding our work in trying to make these renewable energy technologies. So first of all, I said that we're going to reverse combustion. So what is combustion? Well, maybe you can put it in the chat what you know about it. I'll tell you that combustion releases chemical energy that's stored in fossil fuels. So maybe you can tell me what that chemical energy gets released. What type of energy does that get released into? And does anybody know what the reactants are in combustion? All right. I see kinetic energy. Yeah, that's correct. Spontaneously combust. Okay, I like that. So what does that mean? Well, so combustion is the reaction between a hydrocarbon, so a chemical that contains carbon and hydrogen. And a lot of our fossil fuels have this type of formula. So they're made mostly of carbon and hydrogen. So when you think of oil, like, this oil barrel here in the bottom right, that's mostly composed of carbon and hydrogen. And this reacts spontaneously with oxygen, with a little bit of flame maybe, and the products are CO2 and water. Okay, and we know that this reaction is exothermic. This is a scientific term meaning it releases thermal energy. It releases heat. And so this reaction, of course, all of that heat that gets released, we can use that to power, our cars or our airplanes, or, our industrial plants, right? Power plants. So, here combustion, we use it to take advantage of fossil fuels. But there are other renewable energy sources on Earth, right, that are much cleaner and much better for the environment. For example, energy from the sun, solar energy that we can harness with solar panels, or wind energy that we can harness with wind turbines, right? But the issue is, how can we store that energy that we get from the sun or from the wind and use it when we need it and in the places that we need it, right? Because not everywhere that we get sun and wind, or that we can build those, solar panels or wind turbines, are the same places that we demand the energy. And so the idea that we work on in our group is trying to use electrical energy that we could get from solar and wind to power the reverse reaction of combustion. In this case, we take CO2 and water and we make a chemical methanol. So that has those carbons and hydrogens, and oxygen. So those are the two products. And this is actually composed, if we break this reaction down, we can break it into two parts. One part that is an oxidation reaction, and that's where water gets turned into oxygen with the liberation of some electrons and protons. And on the other side, we can take those electrons and protons and give them to CO2 to make methanol and water. All right. So this is what we call two half reactions that make up one redox reaction, we call it, where there's a transfer of electrons. In this case, electrons are coming from water and going to CO2. Okay. And so how does that fit into this whole renewable energy idea? Well, we can use solar and wind to power a reactor that does exactly that reaction, converting CO2 into chemicals like methanol. And that can then be put into our economy and make a circular carbon economy where we're no longer emitting lots of CO2 into the atmosphere. And, so we can be at sustainable carbon emissions. All right, so that's the idea. So how do we study this in our lab? This is what the reactor I'll show you in just a few minutes looks like. So it's split into two components that each do one of those half reactions I just mentioned. So here on the left side is where we take CO2 and it gets converted to methanol with electrons that are coming from this wire into our electrode, our cathode, we call it. On the other side, on the right, we have water that's getting oxidized. Electrons are getting removed from water and we make oxygen. All right. And so those electrons can transport through the wire from the right side to the left side. And so this is, and this whole reactor can be powered by electricity, by, for example, a battery. All right, so I think we'll go ahead and answer some questions here at the end and just get right ahead into our lab tour. So today, David, who's an undergraduate in our group, here he is going to show you guys around the lab. So just give me a second to switch over to the phone and we'll give you the tour.
All right, are we rolling? All right, are we rolling?
Here we go.
Here we go. Turn off the sound on the computer. All right, so I'm David. I'm going to show you around the lab today. This is our catalysis room. This is where we do all our experiments to study the reduction of carbon dioxide into useful chemicals. So if you see over here, just to give you guys a tour, we have all our gas tanks. So this is where we'll store the carbon dioxide that we're later going to turn into fuels like methanol. And then if we come back here, you guys, these are all our electrolytes. So when we're doing a reduction reaction in an electrochemical cell, we need electrolytes to balance the charge in the cell. Over here, we have some of our reference electrodes that we use in our cell. And then over here, this is our gas chromatography machine. So when we do these reactions to reduce CO2, to make useful products, some of our products are gases. So this will tell us what we're making and how much of the useful chemicals we're making in our reaction. This is our potentiostat. So this is basically what's providing the electrical energy to facilitate the reduction of CO2. And then finally, this is what Conor showed you. This is our actual electrochemical cell. So if you look here, what we're doing right now is on this, let's see, our left side here, this is our counter electrode. So this is where we're doing water oxidation to oxygen. So if you see all the bubbles that are coming off this counter electrode, it's a little bit dark because this was kind of an intense reaction. The graphite from the counter electrode probably leached into light. But all these bubbles here are oxidized into oxygen. So this is coming due to those electrons that are left over from the water oxidation, and it's coming up here into an electrode here. So if you look off, we probably also have liquid products coming off, and that's what the CO2 is being turned into. So we have these gas products, and then in the electrolyte, we also have fuels like methanol that's being produced. So if you look at the bottom here, we have this little catalyst layer that's facilitating this. If you guys took high school chemistry, you probably know what a catalyst is. Basically, these are our chemicals that we're using to lower the amount of energy we need to drive forward this reaction of CO2 to our useful products. And then basically what we're doing is we have CO2 to our cell, it's getting reduced into our useful products, and then we're quantifying how much of our product we're making through this gas chromatography machine, and we'll later figure out how many liquid fuels we're making by taking a sample of the electrolyte later. So this is our cell. This is basically how we do our conversion of CO2 into useful products to try and facilitate this circular carbon economy. Finally, we also have this cool other setup here. So instead of electrical energy, we can also use solar energy to turn CO2 into products directly. So this could be useful because then instead of collecting energy somewhere else, we can just use sunlight to directly turn CO2 into useful products. So this lamp here is our solar simulator. The idea is that we can simulate the sunlight here so that one day we can use the actual sun to do this reaction. And then we have also this electrode here, which is made of silicon. And silicon is interesting because it's a semiconductor. And when the sun, so it only conducts when it has enough energy to excite the electrons off the silicon. So what we'll do is we'll take the solar simulator, it'll shine light onto the silicon, and then we'll get electrons that come off the silicon, which will create a voltage and will reduce carbon dioxide into our products. So if you see here, what we're doing is we're turning on this lamp and it's going to excite the electrode, and we're going to basically use this energy from light to turn carbon dioxide into fuel. So it's pretty crazy. You can just take energy from light and store it directly into these bonds in our fuels that we're making. So that was our lab tour. Thank you so much for listening to us. And I think we have some time for some questions.
Great. So now we'll get back to the computer maybe and answer some questions.
Fantastic. Yeah, thank you so much for that tour. Add you back spotlight. Okay, awesome. Yeah, we have a couple questions. I think first, could you guys talk us through a little bit more of like what a catalyst is? It sounds like some people have learned about these in school and some people haven't.
Yeah, that's a great question. So the catalyst is actually what our lab is most interested in of this whole process. And what the catalyst does is it makes the process happen faster, the reaction happen faster. So it reduces the sort of energy barrier required to make the reaction happen. And so you might wonder, like, how does that work, right? How can a catalyst do that? And so the way it works is it can interact with the reactant. So in this case, CO2. So CO2 can, for example, bind to your catalyst. And when it binds to your catalyst, it makes it much easier for those electrons to get transferred to the CO2. So it sort of activates the CO2 molecule to be converted. And so, of course, that's really interesting. And it's something, you know, that many labs, including us, are focused on. How can we design catalysts that do this better and faster, and to make even more useful products? Yeah, good question.
Yeah, I guess going off of what you just ended with there of useful products, you had mentioned methanol as the product that you're creating. Are there different types of fuels that you could create using a similar process?
Yeah. So there's a few different chemicals, and right now, because of we don't know too many catalysts that work for this reaction very well. So we're kind of limited to only a few products, you know, maybe just a handful. Some of them are maybe ethanol, which maybe you've heard of, and methanol, which we focus on in our group. But there's also ethylene. Some people can even make propanol. And so those are all useful, you know, chemicals that could be used as fuels. But there's still a lot of research into trying to make even more energy dense products.
Awesome. And then another question that we had that maybe both you and David could answer just like in like 30 seconds or so. But if you could each tell us kind of like what brought you to this lab, and like, yeah, maybe when did you start studying chemistry and what made you interested in this?
You want to answer
All
that?
right. Well, I mean, what brought me to the lab was I thought we were doing some really cool research here, you know, with like all the CO2 emissions out there. And, you know, it's a big issue. And what's cooler than, you know, turning CO2 into a liquid fuel, especially given all the challenges with all sorts of different energy sources. So what I really liked about this chemistry lab is that you can see a connection between like the chemistry and the use for it out in the real world. So I think that's really cool that we can start to pilot these reactions that can start to solve some of the problems that we're going to be facing in terms of energy going forward. So I thought that was really cool.
Yeah, for me, I think, when I was in high school, I had a really great chemistry teacher, Mr. Dupuis, and he really kind of inspired me to study chemistry. And so that was a big sort of a turning point for me. I really liked learning about chemistry. And so I went to college and I studied chemistry. And from there, I knew that I thought energy was a really important and, huge sort of global challenge that we face, as people. Like, how can we make, and store energy in an effective way? And so that's kind of why I ended up working in this group. And I really enjoyed it. And I hope a lot of you go on to study not only chemistry, but science in general.
Fantastic. Yeah, that's really cool to hear about what drives you to do what you do each day. Okay, I think at this point, I'm going to turn it over to Vimig, who's going to tell us a little bit about the other exciting events that we have coming up in the next few weeks and months. So thank you so much, Connor and David. Really appreciate it.